Hey, what do we got? Okay. Let's finish our discussion. Tides. We'll look at how we spin down, spin up a body. And then we'll talk about the other tidally locked body in the solar system, the tidally locked planet. And I'll update the slides. Question before we start. I did homework 2 then. That good?
No, not really.
Not good. Not good.
Could be better.
Okay. Could have been what?
Could be better on my end, but.
It's fine. Okay, we were talking about torque. So this is the thing we want to calculate today. N. The F was the easy part. Sorry, the R was the easy part. The F we just calculated using law of cosines. Okay. We made an approximation. The approximation was that little r compared to big R. This sort of in there. It says that the total distance usually significantly larger than the size of the body itself. Big R. So this ratio here less than 1, right? Big R. And then things of order that power square and so on and so forth, we can drop them like we do in computation. Okay. So this is the force of the nearest bulge. And similarly, the force on the other bulge is the same, except for a minus sign. So here's the far bulge. And you gain a minus sign here because of the additional. So if you define the angle here as theta, and this one is theta plus pi. Cool. Okay. So we're almost there. So now we've defined the forces, and now we just have to look at the torques. So let's do that. All right. Draw a picture again, just to make sure we understand it. So here's your body up here. This one is R. Okay. And I'm going to keep projecting that line all the way out. Then I'm going to draw a bulge. These are exaggerated. Remember that these bulges do not at all show how large they are. Right? They're small. Perfect. And then we have the angle theta between these two. And the distance here to our body, we call Rn. Why is it Rn?
Near bulge.
Near bulge. As opposed to this one over here. Assume that's a good drawing. This is R for R bulge. Good. Okay. Good words. All right. And this is all with respect to this R, which is the one that we normally consider. How far away is the object from the body that it's orbiting? Right? That's the one that we want. Or that's the one that we know. These are the ones we want to know. Right? Okay. Okay. So in order to find the torque from, say, the near bulge, we have to look at sine of alpha. So that's this angle right here. Why is that? How would I want to sine of alpha?
Or that it's the angle adjacent to that distance.
Right. So let's remember how torques work. Okay, so here's the body that I'm trying to rotate, right? Okay. So where is R? What?
Would be the radius.
Yeah, but where? From where to where? You're pointing, but from where to where?
Of the door hinges to the.
From the door hinges to the door, along the body of the door. So this is R. Good. Now, if I want to close the door, I press which part of the door? This side or this side? Okay, so you can't see that. Okay, so let's imagine I want to open it. So this is the side. You want the force to go that way, right? So R cross F. Do that. R cross F. Okay, and then it's rotating counterclockwise. Good. Okay. So then we have to ask the question, what does the cross product really mean? Because if I try this way, can I close the door or open the door? No, I can't create torque in the same direction. Similarly, if I try to push it this way, can I open the door? No, right? That's the wrong direction, right? Because that's going to want it to rotate down or up. That's not going to happen, right? So there is, in fact, R cross F has a product. You will remember for R dot, or A dot B, we use what property? What trigonometric property? Vector A dotted into vector B is equal to A, B, should sine theta? Which one is that? Cosine theta, right. So what does this mean? What does that mean in English? That's math, but what does it mean in English? It's English, right? So, okay, so let's draw it. Okay. Let's say this is A. Let's say this is B. Let's say this is theta. Now what does it mean? Uh, that's not exactly what I'm asking for. Dot product represents how much of A is in B or vice versa. Okay. So if we change this angle and we align them, then cosine of theta is pointing in the same direction. 0, right? Because cosine of 0 is 1. Okay. So if we align them, then theta is 0 and the product is 1. All of A is inside of all of B. They're in the same direction. Okay, similarly, if they're perpendicular, what do I get? None of A is in B, or vice versa. Right? Okay, this is how you think of dot products. How much of one vector is in the other vector? Does that make sense? Okay, so now let's do the other one. What's A cross B.
Orthogonal vector components.
Exactly right. Exactly right. And I would use those words too. So I'm gonna write that in a second, but what is the math?
Find the determinant.
No. Too complicated. Just look at it. Just look. It's simple. You could guess. Bingo. Okay? A, B, sine theta. And what this represents, just like what David said, is how much of A is orthogonal to B. Okay, if they're aligned, what happens? Right. So I can't push that door. I can't create torque if R and the force are in the same direction, right? And I maximize that torque when they're orthogonal. Okay. So now, why the heck do we need this alpha? How much of this torque is on fire? All right, so there's my alpha. You can also write it in terms of pi minus alpha. That's perfectly fine. So I would write it on the side. Okay, and I'm just going to use the law of sines here. You all like the law of sines. You remember the law of sines? What's the law of sines do?
The law of sines is, say, A over, sine of alpha is equal to B over sine of beta, which is equal to G over sine of gamma.
You can flip them. It's not illegal. So if you write it as sine over A, that's okay. Good. Law of sines. Look at that math we have today. So we'll use law of sines here to relate the thing we want to the thing we have, which is sine theta. Okay. And as we do that, we find that the sine of alpha here can be written like this. See if this sort of fits with what we're working with in our head. So you have some tidal bulge, right? That's this angle here. Oh, I wrote it wrong. Sorry. Let's write it in here so that it's not overlapping. It's this angle. It's the same distance here. But I want to draw the distinction between alpha. Alpha is just between our line and the line from the body, right? Because the R that we're working on, if you think about what's the distance from here to here, right? That's the angle R versus that, which is being attracted. So the cross product between these here. You can also do this one, pi over I could say. Here. Come on. Okay, so let's imagine we rotate the bottom. So that the angular bulges are perfectly aligned with M. How much torque do I create? Before you say it out loud, think about it. All right, you understand the question? So we rotate the bulges so that they're both pointing exactly at the body. How much torque do I create? Don't create any. Is that true? Okay, let's take a step back. How do you create torque? Good. So N is R cross F. Show me where R is. Well, let's be a little careful here. This is the center line between them. But which object are we turning?
Oh, this,
Good.
so,
Yeah, so that bulge, right? So good. So that's this one here. All right, and which one is F?
the. This,
Good. Okay. So now let's rotate this to here. Such that the angle is 0 and the bulge points along this axis.
you need to get them octagonal, but you can't change R, so you have to.
Well, hold on. I'm just asking, the question I'm asking is there torque? How much torque is there? So if I am aligned here with the bulges aligned along the line that points to the moon, do I get torque? No, why?
Because you need some sort of like orthogonality to have it, but because they're both aligned together, there's no way that.
So you pointed this one, and you said, once I place it on the line between them, and the line between them is this one, so this one goes down and this one goes down, right? They go together. But you know, same way out. So this one is the rotating body, and this one here is the force, right? So they start up here, they come down to there. And once they're like that, you get no more torque. Right? Okay. So let's see if that's true. Here it is. So I said that we want this near torque. I made a weird claim about signs. I said we're going to use R, which is the body R, and we're going to use the near force and the sine of the angle between them. Good thing we figured all that shit out already, right? So it's up here. Bada bing, bada boom. Now I have this piece. R is right here. This is the near force that I just calculated. Swoosh, right there. And then I have this one. Sine alpha. And that's that long one that we just calculated, although you didn't calculate it, but you can do it at home if you want. Okay. So let's clean this up a little bit. Bring this thing, I'm gonna put it right in here. So it's GNM big R sine, right? That comes up here, that comes over, and then that's over on the right. And it's the product of this thing plus the product of this thing. How did I get this thing? Well, this one is 2 big R over little r. This one is 1 R. So how did I get this term? Is this exactly right?
The other one with the 2R over R, that's like a big number on the bottom, or there's like a big number involved, so you can kind of just like ignore it.
Right. So let's have a look at this. This is something that people love, right? We have 1 plus A times 1 plus B, right? What's that?
A squared plus 2AB.
A squared?
Oh, 1 plus
1, because it's this times this, plus, let's do this at a time. It's not 2AB. It's B plus A plus AB. See how that's different? Okay. So this is not your quadratic equation that everyone knows and loves. But let's see if it makes sense now. So if I look here, I have this one is let's call this my 2R over little r. And let's call this my R over R. And then this one, of course, is the product thereof, which is 2R over little r times R over little r. And to Dante's point, this thing really looks like get out. R over little r squared. We already said hate those. They're not my friend, don't ever want to see them. So this is gone. Right? So this is approximately equal to, you'll notice the sign now, 1 plus 3 r over little r. The sign. Okay. Same all. Okay. This is important. When you're doing planetary science, when you're doing any type of physics, you have to think about leading terms and what's the most important modification to that. Okay? Don't just do algebra because algebra is required. Right? Have a look ahead of time. Say, oh, if I write this, right? For example, let's say you didn't distribute, or you took these r's and you put them in there so that you had like an r over here and some r's over here, and you put these r's in over here. You would automatically be setting yourself up for failure because you're not able to see what each of the terms' contribution is to the physics. This thing up here behaves like, almost exactly like GMM over something that's R-ish. This behaves exactly like a gravity. And this is a modifier. That is an angle-based modifier. Okay. Okay. Does this process make sense? Why we would do this? You want to be able to make these simplifications and justify them while you're working. Okay. We're not mathematicians. Leading terms are fine. Okay. So let's have a look at this near torque. That's just for the near torque. Remember, we still have to calculate the far torque before we know the net torque. Because it could well be that we did all of this for nothing, and the torque is canceled. Right? It would be very silly. That's what not what's that. So let's look at the right-hand rule. So if I do that, let's start with let's go R that way, and then F is going that way, and the torque is going into the board. And that's what this little cross. The feather, the arrow. Okay. Good. So which direction does the near bulge cause the planet to spin? Counterclockwise. Is that right? Have a look. R cross F creates rotation in which direction? R cross F. So this is up. That's counterclockwise, right? Up out of the board. If I look at it from above. You see what I'm saying? Let's have a look. Here's the door. Oh my God. I got caught. Got caught. Okay, here's the door. Viewed from above. Here's the door hand. It's a pretty good door, actually. I'm not gonna lie. All right. There is R. There is F. R cross F out of the board. This is out of the board and results in a rotation counterclockwise. Good.
So that is the clockwise.
Right. Too long. Good. Let's try again. All right. Let's start here at the door. And here's the handle. And I'm pressing on it this way. R goes this way. F goes this way. R cross. Wait. Ah, interesting. Okay, so this is which way?
That'd be.
No, which direction is the torque? I'm just asking for direction. R cross F.
Yeah.
So do that here. Tell me which direction the torque is going. Any of you can do this. Okay, what do you see? R cross F. Inward. R cross F. Your thumb is naturally going to point. Always just stick with one and then rotate this in the direction of the other one, and your thumb follows. Doesn't unless your hands are real broken.
What do you mean by like inward?
So imagine, if you will, this is a 2D plane, but imagine I had a beautiful 3D drawing board. Right? I go in this direction and this direction, and my thumb, if it could, would point through the board, into the board, as opposed to if I go this way and this way, it points out of the board. Right? So the reason we use this terminology is because if you imagine an arrow like that, really good arrow, Krismani, you're such an artist. Okay, how do you view the arrow? Well, if you view the arrow coming at you, you just see the head of the arrow. If you view it going away from you, you just see the crosshairs. Right? So this is out. This is in. All right. Now, let's finish the talk about torques because it's really important. This one rotates in which direction? Clockwise. Okay. So finally, inward torques produce what kind of rotation? And outward torques produce? There we go. Sorry, it's so many letters. I'm such a bad speller. Okay. What?
Just shorten it, CCW, CCW.
Oh, stop it now. That's not, we don't so many things, then you get more confused and have to explain it a third time. I write it once, I can just leave it there. Yeah. Okay, so yeah, so this kind of picture is beginning to make sense, right? So what is the bulge doing? It's getting pulled in the direction where there's no torque. Right? Good. All right. What do we think is gonna happen on the other side? Let's remember one thing here, right? That other bulge is also being pulled, right?
So does that mean the other side is being pulled towards the, towards where there's more torque?
Right, yeah, so that's a very good question, right? So the near side makes a lot of sense. We pull the thing, it comes closer. The far bulge is a little bit fucked when you think about it. Because as I rotate this body, let's say I wasn't pulling on this, as I rotate this body, this moves away from the thing that's pulling it. So this thing wants to get pulled over here. Right? Okay. Interestingly enough, that one is directed out of the page. This one's into the page. That one's out of the page. Which way does that rotate? Does it make sense? This one is being pulled this way. This one is being pulled this way. One more thing that I want to point out to you. Note the sign. This sign is a holdover from this part when we calculated the forces. Right? So if these are both pluses, then this becomes plus. But for the forces on the far side, they were both negative, and so they're both negative here. Okay, now we get to the grand finale. Right? What do we want? We don't care about the individual torques. So in F, we calculate it up. We want the net torque. What was the point of doing this whole exercise? Do you remember why we even started talking about this? Yeah, we were talking about this thing where why does the moon show the same face? What is happening to these planets that are interacting with one another? We, for example, saw Io showing the same face to Jupiter. In fact, all 4 of the Galilean satellites are tidally locked to Jupiter. How did this happen? How quickly does it happen? Right? What is this process? I made a grand presumption. I said, without any evidence, that the moon would rather fuck off to infinity than hang out with us until we slow down to show the same thing. You will be able to calculate that by the end of today, I hope. We'll find out. Okay. So here's the net torque. Okay. And you're just going to add them. They're vector quantities, so they can be added. Right? One thing that we got to do to be a little careful here. So they're vector quantities. And the near plus the far, they have that same term in the front. Right? Yeah, why is it a negative? Okay, let me ask you to do a different thing. I want you to write this down to make sure your brains are following along. Come on. Okay, write down this one. Don't, take this piece right here. Take this piece, call this call this big alpha. Okay, so let's write that the near torque is alpha times 1 plus 3 r over little r cosine theta. And I would really like for you to finish this as a vector quantity. So tell me what you would have to do here and here in order for this to be a vector quantity. Okay? And similarly, comma, n far is the same stuff, alpha, but 1 minus 3r over little r cosine theta, some extra stuff. Vector quantity. We're good. What do I have to add? Good. What direction is it? Sure. Yeah. Let's call the location. You know, we could create a cylindrical coordinate if we wanted, like r theta z. Right? And so I would say this is z. Right? And what's this one? Okay. And now when you add them, what do you get? Yeah, so the alphas are the same here. So I get 1 minus 1. And then I get 3r over little r cos theta minus minus is a plus. Right? So this is 0. And this is 6. Okay.
Can you explain what happened at Hawthorne? Like, why did we like that when we added the two together?
Well, it's a multiple of both of them, right? So it's still on the outside. Yeah, I didn't copy it. Okay, see if that's right. You're right to me. So as a result of that, we had all this stuff. G delta m little m r over r squared sine theta. So sine theta is the same. The cosine theta we get from that addition, but we also get sine big theta over little theta. There's the big theta over the little theta and the 6. Right? Now we can take advantage of the fact that sine theta cosine theta has an identity, and that is equal to what? Almost there. Over 2. So this over 2 takes the 6 back down 3. Which direction is it in? What rotation? Opposite to the parent's rotation. How did you know that from the map? Negative sign. So if you look up here, right, this one and this one, there's a negative sign. So if we go back, we remember the torque in the board was actually not Z, but minus Z. And then these should all be not positive, but both negative. Okay. Good. So what does that mean? Well, functionally, that means that the torque, the net torque from the body on the parent raised by these voltages is acting to turn it in the opposite direction of the rotation of its original rotation. Another word for that would be so what would we call if you have something that's rotating and it's rotating counterclockwise and you try to rotate it clockwise. What are you going to do to it? Simplest of words here. Stop it. Yeah, you can stop it or slow it down, right? Okay. So the tides do what to the parent body? Slow down the rotation of the parent body. That's all I'm trying to get you at. Okay. We talked about where does this energy come from? Where does the energy of Io to deform the entire interior come to make something that's volcanically active for 4.5 billion years that's smaller than the moon? Where does that energy come from? Good. And again, where does that energy come from? And again, specifically, what on Jupiter? Remember, we have to think about conversion of energy. Is right. Rotational kinetic energy is being converted through tides into volcanism. Okay. Good. Okay. Sorry for the tirade. So far we've talked about planets with the tidal lead, and we're going to use some definitions here. So tidal lead just means that this is a positive quantity. That is to say that the tidal bulge is running ahead of the planet, of the moon. Okay. So what's going to happen is that the spin of the planet will decrease with time. Day will get longer, it'll slow down. We talked about that, right? Interestingly enough, and we haven't seen this yet, you will see this shortly, the angular momentum of the satellite of the moon is going to increase. Right? So let me ask you a question. Does the Earth's bulges, the Earth's tides, do they lead or lag the moon? Why do they lead? Earth is slowing down. That's what I said in Tuesday's class. What else did I say? Yeah, the moon's fucking up, right? And those are the two things that we predict should happen if the moon creating tidal bulges on the Earth, occurs in a leading phase position. Right? Okay. Can I ask you a different question? What would happen if the tidal bulges were lagging?
Pretty far,
Why is that?
because instead of going further from, us, the moon, since we're lagging behind the moon would come slowly get closer to the.
Okay, so let's think about the two things that can happen here, right? So what's the net effect there? And maybe we'll do this as a problem too. You got a body. Let's put the bulges over here. Okay. Now, which direction are the torques?
The near torque would be the lane. Out of the board would be called torque.
Let's check this out. Here. So near torque is now here. So this one cross with that one. It's out of the board. And out of the board means counterclockwise. So the near torque here wants to go that. And out here, is that true? Okay, so here, let's go 1, and then it's pointing back that way, and my thumb is now in the board. In the board, let's put my handy dandy compass. Oh, that one wants to go this way. So that is exactly opposite though. So if I have a tide that is lagging, it's going to act to do what to the rotation of the parent body? Speed it up. Gonna want to speed it up. Okay. And the angular momentum is gonna what? Decrease. Why? Come on, folks. Conservation laws. What am I conserving here? Nope. You are conserving energy, but that's not what I'm asking about. Which kind of momentum? Conservation of angular momentum. Okay. If the planet speeds up, okay, let's do one more thing. Let's make sure that that makes sense. Did I say that? So this is looking at the revolution from the satellite's frame of reference, recognizing, of course, that there are tidal bulges on the satellite as well. And here, generally speaking, you know, you're going to flip around the coordinate system, but the math will be essentially the same, right? We don't have to worry too much about it. The major thing that's going to be different is the delta M in here. This is going to be much smaller, obviously. But this is deeply made up for, oh, I wish I had just written it down. Well, in that equation, you'll see it's delta M and big M. And the big M, of course, is of the other body. And when that other body is Jupiter, that's a big number, right? So generally speaking, we can look at the tides raised on the satellite's body, and this is very rapidly going to cause the satellite to either speed up or slow down, right? In order to match. Okay. So this is why you get tidal locking entirely. Okay? Tidal bulges lead the revolution. Faster rotation drags the bulge away from the parent satellite line. That's perfectly fine. And then tidal torques decrease the rotational momentum. Right? And as they decrease the rotational momentum, they can't decrease it to nothing. Right? What they want is those two tidal bulges to be pointed at each other. So the first thing that happens in almost every situation is that the satellite, which is usually spinning quite rapidly, doing its own thing, first it aligns to the parent. And then it can no longer lose angular momentum from its rotation, and it can only lose it through the combination of the two. Okay? So as it slows down, it increases its angular momentum, and the orbital distance increases. And that's MVR. Good. We're getting that now? All right. For eccentric orbits, this gets trickier, obviously. We did a perfect example during a circle, but if you get closer and farther, the torques get much larger. Remember that they're going like 1/r, so as those distances get smaller, that 1/r becomes much more important. Good. Yeah, if you're closer to the planet, you get to transfer angular momentum. As the orbit gets larger, the eccentricity tends to become more circular. This will actually explain some of the phenomenon that we see in the Jovian system. I think I have some slides on this. This might even be next. All right. We'll talk about the ratio. And we'll talk about how the Jovian system is set up in the first place. Okay, so let's look at the conditions that produce the lag that I was telling you about. So let's imagine for a moment that the satellite has prograde revolution. That is to say, revolution in the same direction as the rotation, but faster than the parent. Does that make sense what I'm saying here? So you get captured, but you're going around the parent body much faster than the parent body's rotation. Okay. Is this common for Jupiter? What's Jupiter's rotation? Pretty fast. 10 hours. Very good. What's Io's rotation? Yeah, like a day and a half, right? So, like, that's not the situation, right? Okay. What's the Earth's rotation? 1 day. What's the moon's rotation? Yeah, 30 is very good. Okay, 28 I'll take. Okay, so it's not that. Do you know any systems where it's like that? The thing orbiting us is going faster than we are.
No.
Yes, or no?
Oh, wait, the ISS?
Ah, how fast does the ISS go?
Like once every 90 minutes or something.
That's correct. Once every 90 minutes, it makes a full orbit of the Earth. So that would be a great example of this, right? Okay, so this is faster than the parent body. This produces a tidal lag. Right? All right. Second one is that the satellite's orbit, let's say it's retrograde. Okay, so let's say it's going in the opposite direction of the rotation of the body. That would be the way for, say, Venus, right? Venus is going in the opposite direction. Let's say it had a moon going in the direction of all the other bodies in the solar system. That would be considered retrograde motion, right? If you have retrograde motion, the bodies will spin up and decrease their distance. Eventually.
So Venus eventually at some point had a moon and did that.
This is a very good hypothesis, and David Stevenson presented this at a conference and said, I'm not going to write a paper because it's intrinsically untouchable, but this is his hypothesis for why Venus is so fucked. He basically said, here's how you fuck Venus over, okay? Legally speaking. Okay. You start with the Venus. Perfectly good Venus, oceans, lots of water, identical to Earth, probably significantly smaller. But it's early. Let's call it 300 million years after the creation of the solar system. Okay, magma surface, everything's great. So there's crap flying around, and there's more crap closer to the sun. There always is. We saw those density plots as they drop off. So there's more material closer to the sun. So that means Venus gets hit. Now that's okay. Venus gets a nice moon. And they're going in the same direction, just like our setup is. Okay? It's a little tilted. Maybe it tilts over to its side. And the moon's like over here going around. But there's more stuff. So Venus gets hit again. And forms a second moon, but this moon is going in the opposite direction. Okay. Think about that, if you will. If Venus is rotating in one direction and the moon is going in the opposite direction, eventually they get close enough and they collide, and the evidence of all moons is gone. Inherently untested.
So couldn't they test that using the same way that they test for the Thea impactor? Because I know there's people trying to test that using volcanic provinces at the core boundary.
Sure, I mean, so you can do that if you can get to the surface. Venus can't get to the surface good, right? If we can figure out how to land on Venus' surface and bring back surface rocks, yes. And more importantly, the holy grail in meteorites is Venus meteorite from right? Early Venus meteorites, or a number of Venus meteorites that show the composition, if it ever changed on the surface, right? You want something at 300 million. You want something at 500 million years old. You want it at 1, 2, 3, and 4 billion years old. Because if that crust never changed, throw this idea out. But if this crust started super hydrated and then changed, and guess what? All the volatiles disappeared too. That was probably not entirely, but it could very well be cataclysmic event. Right? Okay. So this is the holy grail in meteorite mining. This is why you would ever pay money to live on the moon. Sorry, this is going to be a tirade. Okay, so if you want, you know, let's say you run into your favorite billionaire and they give you money to go do an expedition anywhere, and you're like, I want to bring back the coolest, most unique science ever. You say, I want infinite money to go land on the moon and walk around and look for Venusian meteorites on the surface of the moon. It'll require going through a lot of rocks. Most rocks will not be, they'll be moon rocks, but some of them will be Earth meteorites, Mars meteorites, maybe even Mercury meteorites if you get very, very lucky, but very likely Venusian meteorites, because it is one, the closest body to us. People forget that Mars is not the closest body to us. And two, it's been basically chilling since 4 billion years ago. Right? Okay, there's one big event, right? But as long as you're going to walk around, maybe you look for magnetized rocks. Did Venus have a global dynamo at that point? Could you just find them by walking around with a little magnetometer? Or like, what is it called with the, what is it called?
Oh, sorry.
Beep, 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 beep. No, yeah. Could you use a metal detector like you're on the beach on the moon and just go around finding, maybe? Okay. So the chance of doing it high? No. The coolest thing ever? Yes. Okay. Sorry. Tirade. Over. Okay. When Jupiter was formed, oh, right here. Okay. When Jupiter was formed, the Galilean moons were probably formed from the leftovers. That was that disk. We'll see pictures of this or simulations of it when we use that simulations of the galaxies. Probably started in orbits much smaller than they have now, much closer to Jupiter, and they were rapidly rotating. They were rotating in the disk. You know, all the gas and dust is rotating probably 12 or 13 hours. That's quite rapid. So the dust and material inside there that's moving around this object is also not only going to be going around quite quickly, but the individual particles as they come together from that rapidly rotating dust are now going to make planets that are also moving quite rapidly. Okay, they are spinning up really quick, right? Yeah.
Unrelated question. Thinking about Uranus, and could
Uranus?
I'm thinking about it,
Okay.
and could say a series of moons going perpendicular to the axis change the planet's axis?
Yeah. Usually you get rotational axis variations, not from the orbit, but from the impact. So Earth is Robbie Knupp, who is at the Southwest Research Institute, does this modeling with smooth particle hydrodynamics, and she was able to show in like the early 90s that in a number of simulations, you basically are saying, okay, which of these simulations match Earth? And in order to get Earth's 23.5-degree tilt, you have to hit it with a glancing blow. You have to not hit it straight on. If you hit it straight on, you don't get the rotation to change. But if you hit it at the top or you hit it at the bottom, and you kind of hit it not straight on, but like, side swipe it, then you can change the axis. And that's really convenient for cosmochemists because they can also say that in that type of simulation, in the one that you do a glancing blow, that is the one where most of the material, Theia, of the progenitor, goes into the core of the Earth. And the only thing that's flung out, and predominantly the thing that's flung out, is the Earth's crust. So we know from meteoritic data and from the rocks that we picked up on the moon that the moon is mostly made of the Earth's crust. But it's missing a lot of those volatiles we talked about, right? That's been the biggest, like, what is going on with this data. People, when they came back from the Apollo mission, they said, this looks just like the Earth. That's funny, but it's missing all this stuff. They were like, huh, that's weird. I guess they both formed in the same region of space. I don't know. Weird. Okay. But when you have these simulations that show this stuff gets vaporized and the crust is flung off, now you can explain both the orientational axis and the mineralogy. Okay. For Uranus, we won't get that lucky because there is no crust data, but you can get anything to tilt any way you want, like hitting it. The question is, what's the likelihood? Right? Is there other things you can tell? Does it have an unusually large core? Okay. We'll get to this a little bit later. One thing that you'll find out, Uranus and Neptune, not in their original locations. In fact, Uranus probably switched location. So in that shuffle, did the orientation change? That's a very good question. Okay. Okay. It's too many pirates today. We're really happy. Jupiter is formed, they're rapidly rotating, everyone's having a great time, they're all doing their own thing, and Jupiter is like, what are you doing? So very quickly, Jupiter slows them the fuck down. Not their orbit, but their rotation. So they all come to attention, right? They're pointing right at Jupiter. Okay. Now all of them are rotating synchronously, almost instantaneously, right? We saw the effect of that. Okay. And similarly, as they're trading that rotational energy, their angular orbital angular momentum is increasing. Okay, so that's happening here, and they drift outwards. So Io drifts out until it captures Europa in a 2-to-1 resonance, and the system now, okay, can't move past that. Because of this 2-to-1 resonance, when this one tries to, let's say this is Io, and let's say that is that's Jupiter, okay? Let's say they start in, they start moving out. This one hits the maybe 1-day mark, and this one hits the 2-day mark. Okay, then they together get locked. They can still move as a unit, but they cannot. Io can't get closer to Europa. Okay. So now this is, say, 1 day and 2 days. Now they can still move as a unit. They keep moving until they get to 1.5, about 3, and then out here, boom, they capture Ganymede. And that's about 6. Now all 3 of them break. Now they keep trying to move out, and Callisto's out there, and they're like, have fun.
Would they be able to capture Callisto eventually?
Yeah, probably. Probably. I don't know what the rotation. We could. There's probably too many homeworks on this same topic, but you could calculate it quite easily. Not quite easy. You could calculate it quite straightforward. It's not a, you know, a computationally intensive calculation. What you're doing is you're trying to figure out the change in angular momentum, serve quantities, and then, you know, sort of propagate that forward. Say how long until this thing moves out to the physical distance such that these two orbits are in a 2-to-1 resonance, right? And you would just do that between getting and equals. Make sense? Okay, gosh. The interaction of I with Europa with Ganymede, this keeps them out of their circular shape. Right? They're not allowed to be circular. They keep getting tugged and pulled. We will probably talk about this when we talk about resonances in the tidal rings section, but essentially there is a little bit of change in the object of the orbiting object. So you are allowed to trade things like eccentricity and semi-major axis. So I can, let's say I'm being pushed by something outside of me. I can watch this eccentricity go from being almost nothing to being a lot, almost nothing to being a lot, as long as I trade it with other quantities. And that can be the semi-major axis, that can be the inclination. So I can have my whole orbit wobble like this as long as it becomes more and less eccentric. Because of the resonances that all three of them are in, that's a very small amount of trading. You're not allowed to do it as large as, say, Mercury that we'll see. So that pulls it out of their shape, and of course that changes these bodies dramatically, right? This has probably been the case since the beginning of the solar system. Io has been heated like this for 4.5 billion years. So I would like for you to just sit at home. You can calculate this if you want, and think about how big was Io originally. You understand the question? Are volcanoes a net loss? Yeah, for Io, definitely, right? For everyone else, they create atmosphere. That atmosphere, in some cases, gets subducted back into the ground. You know, you can take that as hydrated minerals and rehydrate the crust and everything else. For Venus, you get an 80 bar atmosphere, very thick atmosphere, because you just have outgassing and you have no way to recycle it. And the escape is bad, but it's not horrible. You know, it's not like super rapid because Venus is big. Okay. Think about Io for a little bit. Just imagine, if you will, how big one of these plumes is. You can do a calculation, back of the envelope calculation, see how much it loses just in terms of water weight. Right? How much bigger was Io when it started? Okay. Make sense? Stan Peel predicted this before the spacecrafts ever saw the surface of Io, just based on the orbits. He looked at the orbits, he said they're in resonance, the inner one is eccentric, I predict fall. All right, that's baller stuff. Okay. All right. Do we have time to do this? Yeah, let's just finish Jupiter's moons. I know that this is taking a lot longer than we expected, so that's okay. We'll do Mercury's tides at the beginning on Tuesday. So Europa is next. The rocks in the interior are not molten, but the lower parts of the large crust is of course probably liquid. And we saw the ice pack appearance, we saw the lack of impact craters, we saw the magnetic field measurements from the interior conductive salt water that seems to bend Jupiter's magnetic field. Remember, like a boat flying through the water, we can of course fly over it and notice those deviations from what we would expect. So this may in fact resemble Earth's Arctic Ocean. Go ahead and look up. National Geographic or Planet Earth, anywhere that they have Arctic, subarctic oceans, Antarctic oceans. There's fucking life down there. It's weird and scary, but there's like starfishes and crabs and everything, right? So now I always talk pretty frequently about space whales. Of course, the most likely thing that we'll find there is space crabs or space spiders, because even on Earth, you have hundreds of different species that have individually evolved crab features. Right? This is called convergent evolution. These things are not genetically related, but that's just the best way to get around. If you live in a very high density fluid like water, other than swimming, swimming is quite good, don't get me wrong, but if you need to walk, you're not going to walk on 2 feet. We're quite bad at it. If you ever walked at the bottom of the ocean, the best thing to do is to kind of crawl around on your legs. four little legs. You use the form to be able to swim through water if you need to and get away, right? So this convergent evolution is very popular in all over life. Once one type of creature figures out how to do it, all of them do. So if you're thinking about what probably exists at the bottom of Europa, scraps. Okay. We're sending stuff there, and we'll end with just a slide about the Europa Clipper mission, which will fly in 6 days. So should be fun. Arrives, I think, in 2031. It's going to look for the landing site of the future Europa lander. So in case you didn't know this already, we're going to land on Europa. Not me and you, but maybe you, right? Get into science, get into planetary science in particular, start working on the icy moons. In 2031, we're going to arrive, and shortly thereafter, we're going to send another mission that's going to land on the moon, Europa, and figure out what the fuck these big brown things are. Okay. It's going to look for the ice ocean. We're going to see if it's completely a whole planet or if there's sections that are more dense or less dense. It's going to look at the composition of the ocean and composition of the ice all over. It's going to look at geology, okay, surface features, and it's going to look for recent activity in particular. The reason why this is so important for Europa is Europa does not have plumes, but it sometimes has intermittent activity. So we're going to be looking for, is there places where the crust is thinner? You know, you walk over to there, land near there, and it happens to be spraying by you. You happen to have a machine that can catch what the spray is. Well, now you don't have to dig down 15 kilometers. Cool. I should have said 1 week. All right, sorry folks, keeping you over. If you have any questions, let me know.